PDEC-integrated facade, planning to enhance thermal conductivity.
Okay, so hi, my name is Elisa Martini, and essentially what I'm presenting today is my dissertation, which looked at designing and testing a way to fabricate a facade panel that could integrate PDEC. So, as for most projects, everything kind of stems from buildings that need to, reach more stringent energy requirements, and from also my keen interest in facades and how they can be much more active players in the cooling strategies of buildings. And so, after quite a little bit of research, I discovered PDEC, which stands for passive downdraft evaporative cooling. And this is a technique that's been used throughout the centuries in Middle Eastern vernacular architecture. And how it works is quite simple. Basically, it's passive cooling, which takes the cooling from evaporation to cool air, as well as uses the creation of a current of an air downdraft, which is a consequence of this evaporated water that's now making the air sink. And so my goal then became to try and design a facade panel that could optimize PDEC and then actually test that the cooling potential of this panel. So the methodology was really quite simple. I did a literature review and a case study analysis of how PDEC works and its implementation currently in facades around the built environment. Then I did a few design iterations to try and design a panel. And finally, I tested this panel for its potential. The panel, not showing you at all the design iterations, but the panel that I made at the end of this was quite a simple panel made of unglazed terracotta. And how it works is it's basically, like I said, a 30 centimeters by 30 centimeters panel with a water channel on the inside, which can be filled with water. And due to the fact that it is made of unglazed terracotta, the water can be absorbed and it goes to the other side of the outer face of the panel where it evaporates. And here you can kind of see how I would envision the panel to be used in an actual facade system, with the water being pumped vertically on the top and then kind of being able to vertically flow through and fill the channels on the sides. So, once I made this tile, I tried to actually test it. And I actually tested it right here in Greece. So how I did that was really by setting up a radiative cooler in front of the panel. And I tested the temperature and humidity in the microclimates that were surrounding the panel. And from this diagram on the right, I've tried to show you the microclimates that I've tried to capture. In the blue, so kind of inside this box, and this is, by the way, a cross-section of this experimental setup. So in the blue, what you can see is kind of the internal microclimates, so kind of how the panel affects the volumes of air right on the back face. In the more black area, this would be the external microclimate, so how the air is affected by the most exposed face of the facade panel. And then in the red, the small little sliver of red is just me looking at the surface temperature of the actual panel. So you can see here how my actual project testing rig was set up. And you can kind of see that internal microclimate is enclosed by a rigid board insulation, which is sealed with airtight tape to be able to really isolate that back face. And how I did it was at the end, I did 2 experiments, one dry with absolutely, and this was kind of my control, so no water is in the panel, which means absolutely no evaporative cooling is going on. The second one, I filled both panels with water and ran the experiment. And the runtime for each of the experiments was 2 hours, and obviously the radiant heater is on the whole time, warming the panels. The results are kind of what you'd expect. So obviously there's lower temperatures around the microclimates when there's water added, as well there's also higher humidity, specifically the internal microclimate. And the surface temperature is always lower than the control experiment. So the surface temperature is actually able to always be 8 degrees lower than the actual control experiment. And this aligns actually with findings from other types of facade that implement PDEC. And in my very simplistic calculation, in the runtime of 2 hours, I was able to calculate from the amount of water that was left in the panels that around 10,000 kilojoules of energy had been produced, cooling energy specifically. And so just to wrap it up really quick for you all, the conclusion is obviously that this panel does show an evidence potential for PDEC and evaporative cooling within facade panels in the industry, and the results were kind of as expected. But the limitations, aside from fabrication defects with a lot of leaking, that the size of this experiment is actually a bit too small. So firstly, my experiment wasn't able to measure downdraft created. And this might be because it's too small to actually create a significant downdraft, but it really limits what we can understand of PDEC, because how passive downdraft evaporative cooling works is also very much based on the fact that it can create this downdraft, which could potentially be moved into buildings to help cooling, and generally also helps mitigate urban heat island effect, which is another benefit of using such things on facades. As well, again, because of the size and because of the nature of fluid dynamics, they don't scale linearly. So when used on an actual building scale, the facade would have any sort of downdraft created would also have a much more complex and different behavior to anything that could be tested within the small realm of my laboratory downstairs. The here use laboratory downstairs. And so obviously in future research, any future experimentations, larger rigs and larger scale kind of prototypes would have to be tested outside in the most complex urban environment interaction. And that's all from me. I am open to any questions. Thank you so much for listening.
Thank you so much.